Section: Introduction. In this section, we will discuss the rapid progress of artificial intelligence (AI) technologies and their widespread use in various fields. The effectiveness of AI models greatly depends on having access to large, diverse, and high-quality datasets for training and assessment. However, obtaining such datasets can be challenging due to limited data availability, privacy issues, and the high costs associated with data collection and labeling. Some experts predict a shortage of fresh text data by 2050 and image data by 2060. To tackle these challenges, synthetic data has emerged as a promising solution. Synthetic data is artificially generated to mimic real-world data patterns using algorithms, generative models, or simulations instead of being directly collected by humans. By utilizing synthetic data, we can overcome the limitations of real-world data and enhance the development of more robust, reliable, and fair AI models. Synthetic data offers benefits such as scalability, customization to specific needs, and privacy protection by creating anonymized datasets. Despite its potential, synthetic data also poses challenges. Ensuring the accuracy and reliability of synthetic data is crucial to prevent models from failing to generalize to real-world situations. Additionally, there is a risk of amplifying or introducing biases if synthetic data is not carefully designed and validated. Addressing these challenges requires advanced generative models and evaluation methods to accurately reflect real-world data complexities. In this paper, we review the current state of synthetic data research, discuss best practices, and share lessons learned. The following sections will cover synthetic data generation techniques, applications in model training and evaluation, challenges, potential solutions, and future research directions. Section Summary. In this section, we delve into the effectiveness of synthetic data in training, which mimics real-world data and offers a cost-effective alternative. Various domains leverage synthetic training data, such as mathematical reasoning for language models, where generating synthetic questions and answers, like in Wizard Math and MetaMath, enhances model performance. By combining synthetic data with rigorous verification processes, models like AlphaGeometry achieve problem-solving abilities comparable to human experts, showcasing the potential of this approach in tackling complex tasks. Section: Code. In this section, we explore how synthetic data can enhance various aspects of machine learning. Unlike in mathematics, synthetic data for code reasoning can merge execution results with structured code, as correct code must be executable. In our coding-enhanced models, we introduce Code-RL, which uses an actor-critic approach to enhance pre-trained language models by providing feedback signals on synthetic code samples. We suggest a self-improvement strategy where models create their own synthetic puzzle solution pairs, which are then verified by a real interpreter before being used to refine language models. Additionally, we propose a framework that utilizes a simulated environment and adaptation strategies like self-improvement, synthetic data generation, and COT prompting for code optimization. We have developed Intercode, a framework aimed at improving interactive code generation within a reinforcement learning environment, where code actions and execution feedback observations are utilized. Reflection utilizes external or internally simulated linguistic feedback signals to enhance the code reasoning abilities of language models. In terms of synthetic SFT data, Code Alpaca consists of a dataset of 20K code instructions generated by applying self-instruct to ChatGPT across 21 seed tasks. Wizard Coder introduces Code-Eval Instruct to guide ChatGPT with heuristic prompts to enrich the complexity and diversity of synthetic data. Meanwhile, Magicoder has developed OS Instruct, which generates 75K diverse synthetic instruction samples from open-source code snippets. Synthetic data also proves to be effective in enhancing performance in other reasoning tasks. For example, by augmenting existing natural language datasets with over 500K synthetic examples, model performance on unseen in context learning and algorithmic reasoning tasks significantly improved. STAR generates synthetic chain of thought rationales to refine language models for improved reasoning. In the realm of physics reasoning, Mind's Eye trains a text-to-code model with synthetic text description to rendering code data, enabling the model to convert textual questions into rendering code for execution in a physical engine like DeepMind MuJoCo. This approach allows even small language models equipped with Mind's Eye to achieve performance comparable to models 100 times larger. Moreover, synthetic data is a powerful tool for enabling language models to learn tool-using abilities through simulated trajectories, as collecting real-world human tool-using data can be time-consuming. For instance, LaMDA was trained on interaction data between crowdworkers and the model, annotated with calls to appropriate tools, enabling it to use tools like a calculator, search engine, and machine translator. Similarly, Toolformer and Galactica learn to decide which APIs to call and how to use them by training on template-generated data. Tool Alpaca is a novel framework designed to automatically generate a diverse tool use corpus by simulating multi-agent environments. Furthermore, synthetic data can aid in teaching planning skills to agents in autonomous machine intelligence. By decomposing complex tasks into subtasks and learning to complete them optimally, agents can benefit from feedback signals collected from a simulator. For example, Inner Monologue uses natural language feedback from a simulated environment to teach robots planning skills, improving instruction completion in both simulated and real-world domains. Vima creates a multimodality simulated environment called Vima Bench to compose realistic planning tasks, while Voyager deploys GPT-4-based agents in the Minecraft game to enhance planning efficiency with synthetic feedback. Lastly, in the domain of vision language alignment, synthetic data plays a crucial role in accurately grounding visual input to language models. While web-scraped image caption pairs have been popular, they often lack fine-grained correspondence. Data synthesis pipelines built with image rendering engines can provide more detailed alignment, such as rendering tabular data into charts or converting web page screenshots into code implementation. By training models on synthetically generated data, they can generalize well on realistic data scraped from the internet. Physics engines or game engines like Unity can also be utilized as synthetic data generators to advance computer vision research. Section Summary. In this section, we explore the use of synthetic data for enhancing code reasoning and other reasoning tasks. We introduce strategies like self-improvement synthetic data generation and COT prompting for code optimization, as well as the development of frameworks like Intercode to improve interactive code generation. Synthetic data also proves beneficial in enabling language models to learn tool-using abilities and planning in simulated environments, showcasing its potential in enhancing reasoning capabilities across various domains. Section: Multimodality Instruction Following. In this section, we explore various techniques and methods used in natural language processing research. We discuss the importance of multimodality instruction following for downstream applications of multimodal language models. These models require the ability to reason and follow instructions. Creating data for such tasks can be costly and time-consuming. One approach, LLAVA, leverages image captions to prompt GPT-4 for generating diverse prompt answer pairs. During training, images and prompts are used as input, while caption and bounding box information can be hidden. Additionally, other sources of image attribute information like object bounding boxes, OCR, and derendered charts can be incorporated into the data pipeline. Another important technique discussed is back translation augmentation, commonly used in multilingual language models. This method involves creating synthetic parallel training data from monolingual sources by translating target data into source language data. Researchers have explored different sampling methods for back translation and emphasize the significance of the quality of synthetic data for optimal performance. Furthermore, we delve into generating multilingual questions and answers at scale. Studies have focused on creating synthetic multilingual question-answer pairs to enhance language models' performance in multilingual question answering. Techniques include translating existing monolingual questions-answers, using question generation models, and jointly generating questions and answers in multiple languages. Moreover, we discuss the use of synthetic data for training instruction following models, especially in scenarios where real-world data is limited. Various projects like Self-Instruct, Stanford Alpaca, and EVEL Instruct leverage language models to generate instruction following data. These efforts aim to improve model performance in natural language processing tasks. Additionally, we touch upon mitigating hallucinations in language models through supervised fine-tuning and synthetic data generation. While synthetic data can enhance model capabilities, they can also induce hallucinations if not applied correctly. Recent work has shown promising results in mitigating hallucinations using synthetic data, highlighting the importance of careful application and evaluation of synthetic tasks. Section Summary. In this section, we explore the use of synthetic data for training instruction following models, multilingual question-answer generation, and mitigating hallucinations in language models. We discuss methods like back translation for data augmentation, leveraging synthetic multilingual QA pairs, and using reward models to reduce sycophantic behavior in models. Additionally, we highlight the importance of balancing the quality and diversity of synthetic data to enhance the performance of language models in various tasks. Section: Aligning with shared human preference and values. In this section, we discuss aligning with shared human preferences and values. We explore a method called reinforcement learning from human feedback, RLHF, that involves training a reward model with human data to guide the optimization of language model generation. To address challenges like costly human annotation and varying quality, we propose using a mix of synthetic and real human data to train robust reward models. By using synthetic data, we can generate diverse and large-scale training datasets inexpensively, allowing for thorough testing of AI models' alignment with human values before real-world deployment. However, it's crucial to improve the quality of synthetic data to avoid vulnerabilities like deceptive behavior in AI systems. Factuality evaluation ensures that AI-generated content aligns with factual knowledge. Early methods focused on lexical overlap, while newer model-based approaches consider semantics but still have limitations. Combining language model generation with knowledge graphs can create synthetic evaluation data for factuality assessment effectively and affordably. Red teaming is a valuable technique for testing AI model safety by simulating diverse scenarios to uncover vulnerabilities. Synthetic data can be used to trigger backdoor attacks on AI models, revealing deceptive behavior that standard safety training may not detect easily. Synthetic judgments from large-scale language models can serve as efficient alternatives to human evaluation in various tasks. Benchmarks like AlpacaEval and Mountbench assess LM-based chatbots, while frameworks like CRUXEval and CodeMind evaluate code reasoning abilities. These evaluations based on synthetic data show strong agreement with real human judgments. Section Summary. In this section, we explore the use of synthetic data to align AI models with human values and preferences efficiently. By leveraging synthetic data to simulate various ethical dilemmas and social norms, researchers can test AI systems for alignment with human values before deployment. However, it's crucial to continuously enhance the quality and diversity of synthetic data to address potential risks like biased behavior and deceptive actions in AI models. Section: Challenges and limitations of synthetic data. In this section, we discuss the challenges and limitations of synthetic data. We recognize the importance of being aware of the potential issues that may arise when using synthetic data. Misusing synthetic data can spread false information, which is a major concern that needs to be addressed to ensure the responsible advancement of AI systems. AI models are becoming more adept at creating data that resembles human-generated content like text, images, songs, and videos. However, using synthetic data to impersonate real individuals, sway public opinion, or influence political processes can be risky. It can also lead to a loss of trust in reliable information sources, making it harder for people to differentiate between truth and lies. To tackle these challenges, it is essential for researchers, developers, and policymakers to establish clear guidelines for ethically generating and using synthetic data and to have effective methods for detecting and countering synthetic misinformation. Moreover, the use of synthetic data in aligning AI models, such as constitutional AI, can introduce uncertainty and ambiguity. AI alignment aims to ensure that AI systems behave in line with human values and intentions. However, synthetic data, being artificially created and not sourced from real-world data, may not accurately capture the complexities of human values. This mismatch can result in AI models learning from biased or inaccurate data, leading to behaviors that do not align with human expectations and may cause unintended harm. Addressing these risks requires researchers to carefully consider the limitations of using synthetic data in alignment research and to develop robust ways to validate AI models trained on such data. Furthermore, training models with synthetic data presents challenges in fair evaluation. Evaluation benchmarks are often based on public text sources, which may overlap with the data used for model training. Detecting such evaluation contamination is difficult when models are trained with synthetic data, as the synthetic data may contain rephrased versions of benchmark data. To address this issue, advanced techniques for detecting evaluation contamination are needed, along with the creation of protected evaluation benchmarks to ensure the integrity of the evaluation process. Looking ahead, there are promising avenues for future research in the field of synthetic data. Exploring the scaling laws for synthetic data can help determine the optimal balance between quantity and quality of synthetic samples, especially in training large-scale language models. Additionally, improving the quality and diversity of synthetic data through advanced techniques like generative adversarial networks, GANs, can open up new opportunities for privacy-preserving analysis and model training across various domains. Section Summary. In this section, we highlight the challenges and limitations associated with synthetic data, emphasizing the potential for misuse in spreading misinformation and causing ambiguity in AI alignment. To address these risks, it is essential for researchers, developers, and policymakers to establish ethical guidelines and robust mechanisms for detecting and countering synthetic misinformation. Furthermore, the use of synthetic data in model training poses challenges to fair evaluation, necessitating the development of advanced techniques and protected evaluation benchmarks to ensure the integrity of the evaluation process. Section. Towards high fidelity and more efficient scalable oversight. In this section, we discuss the importance of high fidelity and efficient scalable oversight for complex AI models. As AI systems become more advanced, it becomes harder to monitor their behavior using traditional methods. One potential solution is to explore the use of synthetic data for oversight. Current methods focus on simulating specific scenarios like debates or reflections to generate synthetic data. However, there is a need to cover a wider range of scenarios and modalities to improve the oversight process. Moving forward, a key direction is to achieve scalable oversight more efficiently by leveraging synthetic data. By having control over the generation of synthetic data, we can provide more targeted oversight using less data. Synthetic data will play a crucial role in ensuring trustworthy oversight of AI systems, which is essential for their safe and accountable deployment for the benefit of society. Furthermore, we delve into the concept of self-improvement in AI models through synthetic data generation. The idea is whether a model can generate data better than its original training data, leading to self-improvement. This capability could enable AI systems to enhance their performance by learning from the improved synthetic data. While there has been progress in this area, there are still unanswered questions about the limits of self-improvement and why it is effective. Future research should explore the theoretical and practical aspects of self-improvement through synthetic data generation in various scenarios to understand its conditions, limitations, and risks better. By harnessing the potential of self-improvement capabilities, we can facilitate more efficient and autonomous learning processes in AI systems.